So, have you ever actually stopped to think about how we quantify the physical space around us? I mean, whether you're, buying a new rug for the living room, putting up a fence in the backyard, or even just wondering how your car tracks its mileage, geometry is literally running the show behind the scenes. Welcome to today's Explainer. I'm your host, and today we're going to demystify the math of physical space by looking straight at the textbook fundamentals. All right, let's jump right in. Okay, here's our game plan for today. First, perimeter and area defined. Then, tackling triangle formulas, calculating complex quadrilaterals, unlocking the secrets of circles, and finally, applying these formulas to real life.
Kicking things off with Section 1, perimeter and area defined. Boundaries versus space.
Let's get the absolute basics down. Perimeter is really just the total length of a flat figure's boundary, right? It's strictly one-dimensional, so we measure it in standard units, think centimeters or meters. If you walked all the way around the edge of a local park, that exact physical distance is your perimeter. Area, though, that's the actual surface trapped inside that boundary. Because it's two-dimensional, it's always measured in square units, like square centimeters or square meters. Now, here is a massive red flag straight from the source material. Do not mix up a square meter and a meter square. A square meter is simply an area, but a 5-meter square, that actually means a physical square where every single side is 5 meters long, which gives you an area of 25 square meters. Seriously, don't let that trick you on a test.
Moving right along to Section 2, tackling triangle formulas, three-sided math.
Okay, so we all probably remember the classic formula, right? Area equals half the base times the height. But the absolute crucial detail here is what we actually mean by height. You can literally pick any of the three sides to act as your base. That's totally fine. However, the corresponding height, also known as the altitude, has to be the straight line drawn from the opposite vertex directly down to that chosen base. And here's the kicker. If it is not hitting that base at a perfect 90-degree right angle, you absolutely cannot use it in the formula, period.
But what happens when you're stuck on a problem, you only know the lengths of the three sides, and there is zero mention of the perpendicular height? Well, enter Heron's formula. It is a brilliant little workaround. First, you just calculate the semi-perimeter. That's exactly what it sounds like, the total perimeter divided by 2, which we call S. Then, you take the square root of S multiplied by S minus each of the three individual sides. I know, it looks a little intimidating at first glance, but really it's just basic arithmetic. And it totally saves you from having to figure out any complex angles or missing altitudes.
Now, some special triangles actually hand us some really nice algebraic shortcuts. Take an equilateral triangle, where every side is exactly the same length. Because it's perfectly symmetrical, the perpendicular height slices the base perfectly in half. This means we can skip calculating the height entirely and just use a quick formula built off Pythagoras. The square root of 3 over 4 multiplied by the side squared. Pretty neat, right? And then you have the right angle triangle, which is even better. Its two legs already form a 90-degree angle, so the area is just half the product of those two perpendicular sides. Simple as that.
Up next, Section 3, calculating complex quadrilaterals, four-sided logic.
Let's look at a generalized quadrilateral. It looks pretty chaotic, honestly. No parallel sides, no obvious right angles. But mathematicians are nothing if not resourceful. To find the area of this totally random four-sided shape, all we do is draw a single diagonal line from one corner to the opposite one. Boom! Just like that, we've split it into two normal triangles. The area of the entire shape is now just the top triangle's area plus the bottom triangle's area. You literally just take half the diagonal and multiply it by the sum of the two perpendicular heights drawn to it. We're just recycling the triangle trick we already know.
Of course, a lot of quadrilaterals play by stricter rules. A standard rectangle's area is just its length times its breadth, and its perimeter is twice the sum of those two sides. But what about a parallelogram? Imagine taking a wooden frame of a rectangle and just giving the top a little shove so the whole thing leans over. The formula naturally evolves with it. Instead of length times breadth, the area becomes the base multiplied by the straight, vertical, perpendicular height between those parallel sides. And then we have the trapezium, which sits somewhere in the middle with just one set of parallel sides. The logic to solve this one is actually really elegant. To find the area, you essentially find the average of the two parallel bases. So you add them up and divide by 2, then you just multiply that average by the perpendicular height sandwiched between them. That's it. Half the sum of the parallel sides multiplied by the distance between them.
Moving into some curves now. Section 4, the secrets of circles, infinite sides.
Okay, you literally cannot talk about circles without talking about this legendary number, pi. Whether you write it out as 3.14 or use the fraction 22/7, pi is a universal constant. If you take any circle in the entire universe, from a tiny dime in your pocket to the equator of Jupiter, and you divide its outside border, the circumference, by its straight width directly across the middle, the diameter, you will always get pi. It's kind of mind-blowing when you really think about it.
So, because pi is literally defined as the ratio of circumference to diameter, finding the circumference is super easy. It's just pi multiplied by the diameter. Or, if you're using the radius, which is half the diameter, it's 2 times pi times the radius. For the area, the math works out to pi times the radius squared. Now here's a massive tip, so listen up. Whenever you're tackling a geometry problem with circles, the very first thing you need to do is double-check if the problem gave you the radius or the full diameter. Mixing those two up is the #1 reason people fail these calculations.
Things get really interesting when circles start interacting. Picture a running track, or a ring, made by 2 concentric circles that share the exact same center point. How do you figure out the area of just the track itself? It's surprisingly simple. You calculate the area of the giant outer circle, and then you just subtract the area of the smaller inner circle. It's literally like cutting a hole out of a piece of construction paper. The formula just neatly simplifies down to pi, multiplied by the outer radius squared minus the inner radius squared.
Bringing it all home with Section 5, applying formulas to real life beyond the chalkboard.
We can completely apply that subtractive method we just used on circles to straight lines too. Imagine a rectangular park that's 38 meters long and 32 meters wide, with a paved walking path of uniform width running all the way around the inside border. If you know the area of that path, you can use algebra to find its exact width. You just treat the whole park as one giant rectangle and the grassy area inside the path as a second smaller rectangle. The area of the path is just the outer rectangle's area minus the inner rectangle's area. It's the exact same logic we used for the circular track.
And here's one of my absolute favorite real-world applications. How does your car's speedometer actually know how fast you're going, or how far you've driven? Well, it counts the rotations of your wheels. When a wheel completes exactly one full 360-degree rotation on the pavement, the physical distance it just rolled forward is perfectly mathematically equal to its outer circumference. So if a problem asks how far a car traveled after 2,500 wheel rotations, you just find the wheel circumference, 2 times pi times the radius, and multiply that number by 2,500. Geometry is quite literally how we track our road trips.
All right, to wrap things up, here is your ultimate cheat sheet. We started today with basic 1D boundaries and built our way all the way up to 2D surfaces. We saw that triangles absolutely need a perpendicular height, rectangles rely on those perfect perpendicular sides, messy quadrilaterals can just be broken down into trusty triangles, and circles are all bound by the magic of pi. It's awesome to see how everything connects and builds on a simple foundation of right angles and logical geometry.
So I'm going to leave you with a bit of a challenge. Take a second and just look around the room you're sitting in right now. Look at your desk, the door, your phone screen. Maybe there's a circular clock hanging on the wall. Every single physical thing around you is bound by these exact formulas. So what shapes do you see? And armed with what we covered today, how would you go about measuring their exact boundaries and their total space? Keep that curiosity alive, everybody. Thanks so much for joining me for this explainer. Keep analyzing the world around you, and I will catch you in the next one.